So welcome back, Steve Stumbras. This is the fourth in our series of carbon. This is really a success story from a grower who took a field, decades really of conventional farming, and moved it, transitioned it into organic. Um, in the first three carbon segments, you've heard there's carbon in the atmosphere, there's carbon in all plants. We can move that carbon to the soil in the form of organic matter, and then we can further move that organic matter into soil organic carbon. Big difference between organic matter and carbon, big difference between the work that bacteria can do on the sugar side and what fungi can do on the oil and lipid side, and really getting to carbon. But it's really biology that's the common denominator, the essential driver from every stage to the next. As the advancements occur, it's biology that's really behind it. And then, of course, you heard my oversimplification that all you need is plants and biology to accomplish this. So this is not a recommendation. This is not a segment where I'm going to say you need to do this and this, use this input here. There are just, every farm is different, every enterprise is different. This is not a specific recommendation. What this is kind of a roadmap, kind of an example of how one individual accomplished this. But again, this is going to be completely different for each and every farm, each and every system, each and every piece of property is different. So it's informational, but it's really not meant as a go out there and follow these instructions. That said, I'm happy, we're going to highlight some of this. I'm happy to send anyone the complete rundown on this. There'll be more detail than I'm going to show today, and you can email us or reach out, cell, phone call, and we'll get you the complete document. As I've said before, that building carbon is really about cultural practices and input selections, and that's really true in this trial as well. I mean, by input selections, we really want to select those inputs that are going to be friendly to biology. We know how detrimental anhydrous can be. We know how detrimental high salt fertility inputs can be. So throughout this trial, when you see the inputs that were used, you'll know they were high quality, low salt inputs. There's also, critically important is crop rotation and cover crops. So those cultural practices, along with the selection of the inputs that are going to promote biology, and that's the goal, to promote biology so biology can accomplish the heavy lifting. That's going to be kind of critical. And again, specifics in terms of which products can also be, we're happy to share those if you like. Here is a rundown on the inputs that were used. And real quickly, kind of the overall goals that this grower had in mind going into this project. As you can see, this transition began in 2009, concluded in 2014, and I'll go through just a short summary on a year-by-year basis. So here's what was accomplished in 2009, 2010, 2011, 12, 13, and 14. And of course, everybody is interested in the total costs and what that actually came to on a per year basis. Here's the summary of the cost associated with this work. So now some of the details of what was accomplished. Here you have a graph showing organic matter, pH, and CEC. You can see a 43.5% increase in organic matter. The number, that sounds huge, it's significant, but you're really moving it from 2.3% to 3.3% over the course of that 4 to 5 year period. CEC, you'll also notice a nice jump there, and we'll talk a little bit more about why and how, and obviously that's tied to a great extent to the the loosely held minerals that are able to be easily exchanged by biology. You might have heard me talk earlier, and I'll go into more detail here, but a growing number of agricultural experts are making the distinction between what you can learn from a typical standard traditional test and compare that to what's actually in the tissue. Most of the experts that I talk to do like the base saturation calculations, and you can see those here. The point I think that others are trying to make, and I'll move or exclude sulfur and calcium from this conversation, zinc and boron as well. But there's oftentimes not a strong correlation between what shows up on a test, on a soil test, and what shows up in the tissue of a plant. And really, the driving force there, or the difference there, is you know the the nature of the biology that exists in the system. Robust biology is going to be able to bring plants, or I'm sorry, minerals from the soil that may not show up on a soil test, make them more available to the plant. Some microbes fix, some cycle, some are responsible for root nodulations, but there are those that are responsible really for solubilization. And if you've heard me say before, David Montgomery, one of my favorite authors, in agriculture, he's a geologist, and his line is that the link between geology and fertility is biology. And you're going to see in this next graph, some of that is depicted here. Every soil is made up of different geology, and you can get geological assays for your soil, and that's going to give you a really more comprehensive look at what's in your soil. But in this case, we're talking about phosphorus. And what's depicted here in the red bars is the fact that in parent soils, especially around this part of the country, we're in Wisconsin, there's almost an unlimited supply of phosphorus in the soil. So what we're trying to show here is P2, which some refer to as total phosphorus, and it's not really that. It's the difference between P1 and P2 on a soil test, but it's far from the total phosphorus that you'd find in a geological assay. But that P2 number increased on this field in a very significant way. And it's, I believe, because of the biological activity. The trend in the graph here shows just how much of an increase there was in the P2 number, meaning the available phosphorus number, when this graph here shows the difference between what was actually applied, 78 pounds, and what was increased in terms of availability, 180 pounds. So that difference between 78 and 180, I attribute that to biological vitality. You can also see in the other details that potassium increases, a lot of the other minerals increase. And I mentioned earlier sulfur and calcium. These are highly leachable minerals, and I'm a strong believer that boron, sulfur, calcium, they should be part of a trace mineral fertility program every year. But when you're able to bring a more robust level of biology in your system, you can get a lot more out of your existing soil than you previously received with the assistance of biology. The final fact that we'll look at here is the transition, so to speak, of the microbial makeup in this field. As we've talked about before, root exudates, really once carbon goes from the atmosphere to the plant, from the plant into the soil in the form of root exudates. We've touched on this in other segments. Bacteria can consume sugars, but it takes fungi to consume the oils and the lipids. And you can see in this graphic here how this soil, when it was conventionally farmed for all those years, had a fungal to bacterial ratio, F to B ratio, of 0.27, meaning it was a very bacterially dominant soil. Within a short period of time, again, based on cultural practices and the inputs that were selected, that ratio completely shifted in favor of fungi. So that F to B ratio went to 1.18 in a very short order. And again, if you remember from the previous segments, if and when you maximize the production of root exudates, you can produce, you can produce the sugars, you can process the sugars with bacteria, but unless there's fungi there, that those oils and lipids, that portion of the root exudate, instead of being turned to a carbon, will be oxidized back into the atmosphere. So I think that's really kind of the takeaway here, that plants and biology, bacteria and fungi, good practices, cultural practices, and input selections, and you can really achieve a lot. And we call it a biological flywheel. Getting to a point where the system has got the inertia to run itself, meaning that your plants are productive, they're producing more root exudates, the bacteria is there to process those exudates, and you're growing carbon in your soil. And that's really what's going to make your efforts next year more successful. So thank you very much for tuning in. Again, if you have any questions or you want more details, please reach out. We're happy to help. Thanks.